Okay, so question 1 says 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write only the letter A to D next to the question number 1.1 to 1.6. So in this case, we just said only 6 questions, 2 marks each. For example, 1.7a. Okay, fine. 1.1 says the electron configuration of an element is 1s2, 2s2, 2p4. The valency of this element is what? What will be the valency? This is your question.
Will be 4.
Okay, it will be 4. Snenhlahla, what is your answer?
I'm not sure.
Not sure. So what is valency?
Like the outermost electrons, you know.
The outermost electrons. Okay, that's a good point. At least you have some idea of where we are, and that's good. So you have to think about these things. Don't just be sure that you are not sure, Just think about it because you've already done it a little bit. Okay, I'll draw a quick example here for how an atom looks like in chemistry. Okay, let me just move this more to the center like that. Okay, good. So what we'll have is obviously some protons which are positively charged in the nucleus or in the middle of our atom, and then we'll have some neutrons which do not have any charge. Remember, neutrons like that. So that makes up our nucleus. And then what else we have is electrons that are actually orbiting around our nucleus like this. And then if I draw exactly the configuration that we have for 1.1, then we're going to have 1, 2, 3, 4, 5, 6 on the outside. So when we're talking of valency, let's now see why would our answer be 4? Because looking at this, it looks like I have 6 electrons on the outside energy level. So how do we justify 4?
Also it's 2 then.
Okay, how do we justify 2?
Because like to make it a full orbital and make it balanced, you know.
Okay, I hear what you're saying, but I guess the question can be confusing like this. But when they say valency, not valence electrons, valency, they're basically talking about the outermost energy level or the last energy level. So if I just show my energy levels here, I have energy level, I like to call it N, so energy level 1 and energy level 2. So if I ask you what is the valency of this element, you're gonna say that we find the valence electron on energy level number 2. So the valency is 2. I don't know if that makes sense.
Yes, so
Yes, valence electrons is 6 because we're just gonna count all these electrons here. But valency is the energy level, which is 2. If we went up to 3, say 3s2, then the valency will be 3 in this case. Okay. So option number B will be correct here. So B. Then 1.2, the intermolecular forces holding the molecule in ice together are ion dipole forces, van der Waals, covalent, or hydrogen bond. What intermolecular forces are actually between molecules of ice, or the intermolecular forces that is holding ice together? what are we, how is our interpretation? What are they looking for in this question?
So they're looking for like like the forces that affect like an atom or like a molecule from the outside.
From the outside.
But they're not within the structure, I don't know how to explain.
Did we maybe forget intermolecular forces? Do you remember them?
So it's not like the hydrogen bonding. That's what I remember.
Yeah, but remember, intermolecular forces are actually forces that hold the same molecules together. So if I have, say, for example, carbon dioxide, here is a molecule of carbon dioxide, and then I'll have another carbon dioxide close by. And then there's a force that actually hold this molecule together. It can be from this oxygen to this one or whatever, but this force is what makes carbon dioxide carbon dioxide. Otherwise it would just be flowing around and we wouldn't even tell that there's carbon dioxide.
So,
Water,
so
for
what?
example, there's forces that is holding water together. Otherwise each particle will be everywhere, then we won't be able to tell that it's water. Yes.
So like what are intramolecular forces then?
What are intermolecular forces?
No, intra.
Intra. So the word intra means inside. The word inter means between. So inter is between the molecules. Intra will be actually the bonds that are holding the carbon dioxide on the inside of it. Does that make sense?
Yes.
Yes.
So okay. Oh, I understand.
Okay. So inter is between, and that's the forces that we mainly focus on in grade 11. Intra, they do that in grade 10, but in grade 11 also you do it. That's your covalent bond, that is your ionic bond and stuff like that.
Okay, so the answer here like D then.
D, okay, D is the correct answer, but how do we know it's D?
Because like there's hydrogen and like it's bonded to a smaller atom which is oxygen.
Hydrogen bonded to oxygen, okay. How about Snenhlahla? What is your explanation of why the answer is D? Let's see. So we just needed a good justification.
Is it because hydrogen bonds are the strongest?
Okay, hydrogen bonds are the strongest. All right. The idea I'm getting right now is that we actually forgot intermolecular forces, and that's fine because we've been writing also other subjects. So that is very fine. As soon as we close the lesson, just go to Google Classroom, watch the recording on intermolecular forces. I don't know how many we have already, but I know there's this one that is very, very good, that we explained everything and you guys understood at that time. I think it was in term 1. But go ahead and watch that, remind yourself of that, because you're gonna get few questions on intermolecular forces. Okay, they're gonna come back also in grade 12. But here's what we are dealing with. This is ice is made of which compound actually? Let's start from there.
Water.
Yes, that's where we start. Ice is water. So when you hear the word ice, you know it's water. So I'm gonna have these water molecules, and I'm just gonna draw it like this first. Here is one water molecule, and then there's gonna be another water molecule close by. Remember, ice is more closely packed. So there's this forces, and these forces are now between oxygen and hydrogen. Oxygen and hydrogen like that. And then if I draw another water molecule, you'll see that it's gonna be like that. Oops. And there's also intermolecular forces holding this oxygen and this hydrogen. Same applies to this oxygen, it's gonna be held to that. So every time That's what you get. So this is what making water stick together. And if it's ice, then it's gonna take more energy to actually break those forces, because they are now more stronger, because the molecules are now packed together. If it's just liquid water, then the molecules are more relaxed. If it's ice water, it's called water vapor. Then the water molecules are just freely moving around, and the intermolecular forces between those are very, very weak. Okay. But yeah, if you remember the chapter, you'll remember that any intermolecular forces that is between oxygen and hydrogen is called a hydrogen bond. And that is our strongest bond there is in intermolecular forces. Does
So,
that
so like what is like fluorine, you know,
also fluorine and
nitrogen.
oxygen, also nitrogen and oxygen. Yeah, there we go. So you remember those. So any bond that is between these three, is called a hydrogen bond. Say fluorine can come from hydrofluoric acid like this, and you can have, oh, actually I'm making a mistake. It should be fluorine to hydrogen, nitrogen to hydrogen, and then you have another adjacent HF molecule. So you're gonna have this intermolecular force that is connecting the two, and because it's between fluorine and hydrogen, it's called hydrogen bond. Because it's between nitrogen and hydrogen, it's hydrogen bond. Oxygen and hydrogen bond. Okay. Awesome. So that's just a reminder that you need to revise that work. It's not too much. Just need one recording to actually master the whole chapter. I will also recommend which one to watch. So I'll do the work for you. I'll go and watch a portion of it, because I remember there's this good one that we made at the end of the term. Okay, 1.3, which of the following variables could be used to determine the temperature of a gas in a closed container? Okay, that's a good question. Also, application of intermolecular forces. Let's see which one is the correct option. You have to refer to the definition of temperature.
It's a B.
It's B. Yep, that's correct. Because we define temperature. Temperature is not how hot or cold something is. Temperature is a measure of average kinetic energy. Measure of average kinetic energy. So if we say something as high temperature, what we'll see from our side is that this thing is hot. But what makes it hot is actually the movement of particles. They are moving faster. That makes it increase energy, and that's what gives you the hotness. Okay. So if you remember that definition, so it was going to be easy to identify that B is the correct answer in this case. All right. 1.4, which of the following represents 1 mole? Which one? Supposed to be a little bit easy. Or you can check all the options if you want. So the first one says atoms in 6.02 times 10 to the power 23 grams of sodium. Is that 1 mole? So they gave you, what is 6,02 times 10 to the power 23 grams? What quantity is that?
Isn't the Avogadro's constant?
Yes, but what
Like
quantity?
for particles.
I'll say no, because we have to check the units.
Wait, so says it B then?
Now let's go through the options. So we're still on
Okay.
A. Why what quantity is it? Is it volume? Is it number of particles? Is it moles? Is it molar mass?
Number of particles.
No, that's not
Wait.
correct.
Oh, it's grams. So like it's a mass. Yeah.
It's mass. Exactly. That's what they're looking for. They want to see if you can tell what you are given. Because if you say it's particles, then you can be tempted to say that's the correct answer. But that is mass. And if mass is this, grams, then if I take sodium and find the number of moles of sodium, I'm just going to divide by molar mass of sodium, and there's no way this can be 1 mole. This is too large of a mass. You can check for yourself, but that is not 1 mole. So option A goes away. Then we can look at option B. Option B says the molecules in 22,4 decimeter cubed of water at STP. So it says 1 mole is equal to molecules in that amount of water at STP. Water is not a gas, is it?
But it's listed as STP.
I can take a solid and put it at standard temperature and pressure, but if it's
Oh,
not
so
a
like,
gas, then it's not really affected by gas loss.
but so like, what if it's like water vapor?
Yeah, if they said water vapor, but where I'm standing, I feel like if I say water, I'm referring to liquid water. I'm not sure, but that's what I'm thinking.
So they'll specify if it's vapor or not.
Yeah, they have to specify that it's water vapor, because if it's water, it should be a liquid every time. But if you think about that, molecules and moles, like, the question itself, I mean the option itself doesn't really make sense, because I could have said molecules in 22,4 decimeter cubed of water. Yeah, but anyways, we can go through. Let's leave that one as a possible option. Let's go to number C. 1 mole is represented by the number of protons in 1 gram of hydrogen gas. Number of protons in 1 gram of hydrogen gas. What do we think about that one?
So I don't really understand that one.
Snanhlanhla, can you come in, please? What's your idea? Let's say you're in a test and you get this option here. Maybe if we are unsure, we can even move to D. That's the method of elimination. You're trying to look for 2 options that are definitely not correct and cross them out. The one that you're not sure about, you can leave them and then you can decide after. So D says the molecules in 34 grams of ammonium gas. Ammonium gas. Okay, ammonium looks like this. It's NH4 minus. That's ammonium. And looking at this, there's no way this thing can be a gas. It can only be aqueous. So you see, that's something that is similar to this option of water. So also we can find the number of moles of that, because we are given the mass over molar mass. We can go to the periodic table and check. I think nitrogen is it 14? If you have a periodic table with you, you can check for me. or I can just scroll down to where it is. Okay, so we're looking for nitrogen. It is 14. There it is. So I take 14, I add 4 times 1 for hydrogen. I'm finding the molar mass of this now. So 14 plus 4 into 1. On top, I'm going to have 34, which is the mass. So do we get 1 mole if we do this?
I don't think we do.
Okay, what is the value that we get?
We get
9,8.
1,8.
1,8. Okay, that is not 1 mole, so that option as well is not correct. So this leaves us with B and C, and we can decide which one is correct. I mean, if you check C, protons in 1 gram of hydrogen gas, protons.
wait, so like what if we mix the molar mass? Like ish.
What if we?
Like what makes molar mass? So like what's inside the nucleus or what?
Or what makes the molar mass?
Yes.
Okay. That is what is inside the nucleus, yes. I don't know
So
if...
in hydrogen, is it only a proton or?
Okay, let me go to hydrogen. Let's see what we have on the periodic table. So what does 1 and 1 represent? So the 1 is the atomic number, that is number of protons. This 1 here will basically stand for neutrons plus protons. So neutrons plus protons. You remember neutrons from that sketch I drew that represent an atom. So hydrogen basically looks like this. It's 1 proton and 1 neutron, and then there's a cloud of 1 electron. Okay, so if I say I have 1 gram of this gas, of the hydrogen gas, how many moles do I have from that? Hydrogen gas, I think hydrogen gas is H2, right?
Yes,
Okay, H2. So how many protons do we have in H2? In 1H we have 1, yeah. So in H2 we have 2 protons. And if we find the number of moles of this, it's mass over molar mass. The mass is 1 gram because they say it's 1 gram of hydrogen. 1 gram divided by the molar mass of hydrogen gas is what?
two.
It's 2 because it's 2 times 1. So we get 0.5 moles. This is the moles of hydrogen gas. But what about the moles of protons? You're going to think about this in terms of the ratio. H2 is to protons. The ratio is in 1H2, there's 2 protons. So if the moles of H2 is 0.5, the moles of protons, I'm just going to leave it as X, Obviously, I don't expect you to go through all this trouble for multiple choice, but your mind should be quick at that point. So X is equal to 2 times 0.5. Then the number of moles of protons is 1 mole. A little bit too much, but we get there. I don't know if it makes sense or not.
Wait, so I'm confused. How they two protons in? Oh, my. Okay, never mind. So I understand now.
Okay, you do understand, because in one oxygen there's one proton, in another there's another proton. So in H2 together there's 2 protons available. Does it make sense to both of you?
Yes, sir.
Yeah. Okay, looking at this, I don't think that was a fair question, to be honest. It's a lot to think about, so it's not one of the fairest questions I've seen, because you kind of have to work it out, and it can take a long time. But in the end, let's say you're unsure of even how to start working it out. You see, the work I did here, to me, it's too much. So let's say you were to guess, you have B and C, then you can just have a quick think and just have an educated guess. I mean, the water thing, for me, it disqualifies B, because water is not a gas. So I can't even go to this equation. I can't use that equation. But again, I understand the confusion that we can. It's not specific to say whether it's water vapor or liquid water. So I can see where you can say maybe that option qualifies. But yeah, water, I take it as a liquid. All right, 1.5. The enthalpy in kilojoules per mole for the reverse reaction of the reaction below is what? Okay, this one is like a cool down from 1.4. Should be straightforward. So what is the answer?
D.
Why D?
So because like reverse opposite signs.
Reverse. Okay, remember the enthalpy that you get here is for the forward. Do you agree?
Yes, sir.
All right, so if the forward is negative 120, so it means, by the way, negative 120 represents endothermic or exothermic?
Exothermic.
Exothermic. So this means we are releasing 120 kilojoules per mole of energy in the forward reaction. So if I want to go back, if I want to go in reverse, it means I'll need the same amount of energy. But in this case, or in this time, I'm gonna need to put in that energy, not release it. So it really makes sense that the reverse will have an enthalpy of positive 120 kilojoules per mole. Now it's endothermic for the reverse because we are absorbing energy. So option D is very much the only correct option. The other ones are just like, if you choose B, then maybe that's, I don't know. I don't know how you'd choose the same answer as the forward, but that could be a good mistake. If you choose 75 and negative 75, like, I just don't see how that's possible. So yep, that's how you work that out. 1.6. The process in which acids H plus and bases OH minus react to form salt and water is called what? Is it redox? Is it displacement, synthesis, or hydrolysis?
Redox.
Redox. Okay. Snenhlahla, what do you think?
sure.
Not sure. Okay, which one would you choose if you were to guess? Because sometimes it does come down to guessing. I'm not gonna lie. But it should be a more of an educated guess. Shouldn't be wild guess. So which one?
I'm not sure.
Yeah, not even a guess. Do you say you're gonna leave it blank?
No.
So is there any option that you would have been maybe pulled towards?
C.
Okay, see. All right. So the thing is, you're not gonna even get the same questions in the exam, right? So what I'm trying to do is just to train you to make a decision or to know how you can work it out. And if you look at this kind of question, maybe you're not sure what some of these reactions are. For example, I think you only did redox. You did synthesis, but you might not know that you were doing synthesis reactions. But synthesis is like reactions whereby things are just coming together by forming a covalent bond, in other words. Or you can think of it as just exchanging molecules between each other. So if I have an acid, let's say maybe I have HCl and I have a base NaOH, that is what the question is saying. So what I'm gonna have is NaCl plus water. And this reaction, you can check the oxidation numbers if you did redox reaction, and you'll see that the oxidation numbers do not change, so that disqualifies redox. And then you see that the H plus and OH just combines to form water, and the Cl minus and Na plus combines to form NaCl. So this type of reaction is called a synthetic reaction. But hopefully maybe you don't get a question like that, because you might not be sure. Hydrolysis, you'll do that in grade 12 under organic chemistry and stuff like that, but you'll see how it works. Okay, it's fine. We really wasted a lot of time on multiple choice, but I just kind of want to give an idea of how to go about solving them. It is a lot of marks in this question, just 12 marks, but you can get 20. Okay, question 2, draw a Lewis diagram of methane, just like that. Is it simple or is it hard?
It's relatively simple compared to everything else.
Yeah, okay, so what is the formula of methane? Chemical formula. Because they didn't give it anyway. No one knows. So if you don't know, you can just tell me so that we don't end up wasting a lot of time waiting. Okay, my network disconnected. Let me rejoin. Yes or no?
With NH3.
NH3. Okay, that's called ammonia.
Oh, ish.
Snenhlahla, do you know or no?
Is it CH4?
CH4. Yeah, CH4 is correct. But it's one of the things that you're gonna really do in grade 12. You're not gonna forget it in grade 12 because there's a chapter that is focused on that. But methane looks like that. If you didn't know, then I guess there's no way you could have answered 2.1 especially, but just make sure that maybe you know a couple of common chemicals that they'll ask you about. I mean, methane is one of them. Okay, if I need to draw the Lewis diagram of that, it should be really easy. I check the valence electrons of carbon. How many electrons do we have, valence? I can go to the periodic table if you want. So how many do we have for carbon? It's 4. So you're gonna check this numbers here. This represents your valence electrons, you know, those numbers there in Roman numerals. Where you don't see them, it means you have transitional metals and they can become anything. This one's in the middle. But you can see for carbon is under 4. So everyone here has 4 valence electrons. Okay, if you didn't know that, so go up. So we have 4 valence electrons, so it means I'm going to put each electrons on either side of the carbon. Then hydrogen, how many valence electrons?
1.
1, because hydrogen only has 1 electron anyway, so that's the valence. It's 1 for that, 1 for that, 1 for here, 1 for here, because we have 4 hydrogens. So I just need to draw my hydrogens in now. And there we go. That's the Lewis diagram of methane. No lone pairs. Everything just looks nicely here. Single bonds. And there we go. That's it for this one. You get 2 marks. It's just gonna mark like the correct amount of electrons and the correct shape. Okay, that one is done. 2.2. What is the name of the special kind of bond found inside the methane molecule? In other words, what is this bond called? That one qualifies to be a grade 10 question.
So please repeat the question.
Okay, 2.2. What is the bond that is found inside methane?
Oh, is it a covalent bond?
It is covalent. How do we
But
define covalent
non-polar.
bond?
Is it non-polar?
No. That is something else. But covalent bond, there's a way we define it or the way we understand it. Okay, but
So I don't know.
Snanhlahla, I have to ask you a lot today because you are not speaking. Otherwise,
Is it the sharing of electrons?
yes, covalent bond. When we have a covalent bond, this means there's electron shared between the atoms. So sharing of electrons is what makes a covalent bond. So the carbon and hydrogen there are sharing electrons. That's why they are bonded. Okay, we did a lot of examples on this in the video on intermolecular forces and chemical bonding. So everything is there, literally everything. So A lot of work is on your side. To answer this question, you just needed to say covalent bond, and that's it. Okay. 2.3.1, answer the following questions about magnesium chloride. Also, they don't give the formula of magnesium chloride because it's something that they figure that you can be able to show the formula. So what is the chemical formula of this? It's M okay, this one is not something you can revise, it's just something that you should know. Magnesium chloride, what's the chemical formula?
It's an MgCl2.
MgCl2, yes, that's the one. Okay, 2.3.1, make use of Lewis diagrams to indicate the transfer of electrons between magnesium and chloride. That's like a question you should always expect. We need to show how electrons are transferred between magnesium and the chloride or chlorine to form magnesium chloride. In other words, this is an example of a redox. So what you're gonna do is you'll show that magnesium, let's check the valence electrons if we can find them on the periodic table. Mg has 2 valence electrons. You can see it's under the Roman numerals 2. There it is, right there. So that means we have 2 valence electrons on that. Let's just quickly go and do that. Mg ... then chlorine. If you go and check on the periodic table, maybe let me just go just to convince you. Chlorine is under the 7 Roman numeral, so it's gonna have 7 valence electrons. So they want us to show the actual transfer of electrons. So I need to show that the magnesium is actually going to take 2 of its electrons and give it to chlorine. That way chlorine is going to have more electrons while magnesium has less electrons. Then they're going to be charged, and after they are charged, they attract to form an ionic bond. So this is formed through ionic bonds. And remember, there is a way to find out that it is ionic bond, and maybe that question is there, but let me show you how you were supposed to answer this question. So you show that magnesium on its own is going to donate its 2 electrons to become magnesium. So it's missing 2 electrons, which means it's no longer neutral. What is the charge that it actually gets after losing 2 electrons?
-2.
Okay, that's what I wanted to check. If I lose electron, do I become positive or negative?
Oh, my you become positive. Ish.
Yes, I become positive. So magnesium becomes more positive with a charge of +2, and then it's gonna we're gonna show that it loses 2 electrons like this. Then chlorine is gonna take those 2 electrons. So those 2 electrons go to chlorine. So I'm gonna show that chlorine starts as Cl. And remember, we have 2 chlorines in magnesium chloride. That's why you need to know how it looks before you can even answer this question. So we need 2 of the chlorines to take these 2 electrons and become 2. So each of these chlorine is going to gain 1 electron to become Cl. And then I'm going to show the electron that it gains using a cross. I'm going to put it here in front. and because it gains electrons, then it becomes negative. So I'm going to put that negative there. So looking at this, does it make sense, the whole process? It's for how many? 4 marks. And I promise
Yes.
you're going to get this
So-
question. Yeah, you will get this question for sure. It's there in every question paper that I've at least seen. But that's how you show them. Okay. Then 2.3.2. Remember, if you have a question, you can stop me and ask by just speaking or raising up your hand. 2.3.2, magnesium chloride is an ionic substance. Prove this statement with an appropriate calculation. Okay, it is ionic. Show us by doing a calculation. Which calculation are they looking for? I know if you haven't revised again, I understand you might not remember, but once you revise, you'll see that, oh, this information actually is there, all of it. But if you remember, which calculation are they looking for to prove that this is an ionic bond?
The electronegativity.
Electronegativity, exactly. So you need to find the electronegativity difference. And to do that, you're going to need to find the electronegativity of chlorine. And this will be what we get from the periodic table. So I'll go down to the periodic table and show chlorine. Electronegativity, again, is this value here that is written vertically. So for chlorine, it's 3. For magnesium, it's 1.2. So I'm going to go up. For chlorine, it's 3.0. For magnesium, electronegativity of Mg. Okay, I think I forgot, but it's 1.2 if I remember correctly. Then you're going to take the difference between that electronegativity, and that difference will tell you the kind of bond that forms between the molecule. Whether it's covalent, is it weak covalent, is it strong covalent, is it polar, is it non-polar? You remember those things, and they all form part of intermolecular forces. That's why I say it's going to be important for you to watch the intermolecular forces video. And if I take the difference of these ones, we just call it the change in electronegativity. We just take the bigger number, 3.0, doesn't matter which one, minus the smaller one, and that's equal to 3 minus 1.2, it's 1.8. So there's also notes on that. If the electronegativity is 1.8 or more, then you have an ionic bond. So ionic bond. That's also in the notes. So the main purpose of the lesson is to basically remind you of the amount of work you need to do in order to be ready for the exam. Because now we're doing specific questions, but you need to kind of remind yourself of these things. And you should also ask questions that will help you in that process of remembering the stuff you need to do. Okay, but that's the work you needed to do for this question. So they'll give you a mark for finding the electronegativity and to say that it is ionic bond. So 2 marks in total. Okay, and that's it for question number 2. Question number 3, you can see also on intermolecular forces. So that's like a big chapter in chemistry. They say in the table below, the boiling points of 4 hydrogen halides are given. Hydrogen halides is basically hydrogen and halogen. See, all these guys are from group 17 on the periodic table. 3.1, define the term boiling point. Anyone who remembers? There's like this specific definition, and if you say boiling point is the temperature where a substance boils, that's automatically wrong. There's no way that that is marked correct. That's what someone who's not doing physics can say. In physics, we have a specific definition for boiling point. Anyone? Okay, I'll take it. No one remembers, but boiling point is defined as the temperature at which vapor pressure, I'll just say VP, is equal to atmospheric pressure. Does it ring a bell?
Yes,
Yeah. So you need to remember those as well for your exams, especially if you are writing on Monday. You see, now it looks like you never did physical science, but you need to remind yourself of all these things. 3.2, what is the relationship between strength and intermolecular forces? Strength of intermolecular forces and boiling point. For 1 mark. So one statement that connects, or the what happens with intermolecular forces and how does it affect boiling point is basically the question. Don't let me answer it for you guys. Come on. Say what you think. And we are running out of time, so I'm trying to be quick. Then this one is one of the questions you should actually answer.
When the intermolecular forces are stronger, a boiling point will be higher.
Exactly. That's all you need to say. So the stronger the intermolecular forces, I'll just indicate this with symbols. Intermolecular forces is stronger, boiling point should be higher, because you need more energy or more heat to actually start to break strong forces. That should make sense. That should really make sense. If I say break wood, a pencil, and break a fork, you will find it hard to break a fork because it's steel and steel has strong forces that hold it together as opposed to wood. So that is how intermolecular forces work. And same applies to melting point. The melting point will be high for a strong boiling point. For a strong intermolecular force. Because to make something start to melt, it means you are breaking the forces between it. You are breaking its intermolecular forces. And if they are strong, then you need more energy, which means you're gonna have more melting point or high melting point. What about vapor pressure? Is it high or low for a strong intermolecular force?
it's low.
Okay, it looks like it's a guess, but it is low. You can think of, or the way I like to think of vapor pressure is, I like to say how fast or how much vapor do I get, and if the intermolecular forces are strong, then I can boil water the whole day and I'm not gonna see any vapor because the forces are strong, But if I have something that is weak, I'll just put it on fire and like 2 minutes I now have vapor pressure. So strong intermolecular forces translates to low vapor pressure. Weak intermolecular forces it's easy to boil this thing, so I'm gonna see more vapor pressure. Okay, that's how I used to think about these things. I mean, you should have a method of learning, and that's like what I used to do. Okay. That's the three things that you need to remember in terms of relationship between intermolecular forces and boiling point, melting point, and vapor pressure. Also there in the notes, by the way. 3.3, which of the hydrogen halides A to D in the table has the highest vapor pressure? Okay, there is vapor pressure now. Which of these three have the highest vapor pressure? And they want a reason for it.
So the HCl.
HCl. Okay, what is the reason for HCl?
It has the lowest boiling point.
It is the lowest boiling
So
point,
like,
and that's exactly
so let's
correct.
end the requirement. Yeah.
Yes. So to answer this one, 3.3.1, they also need a reason for that. So the reason is gonna be, remember what I used to say in class is that your reason should be based on evidence, and your evidence is boiling point. Why did you say it's HCl? Because I saw the boiling point. So you shouldn't say anything outside of that. You shouldn't say, you can be tempted to say, it is dipole forces 1, 2, 3, but that's not what you're looking for. You're looking for the evidence. If it's 3 marks, then the first reason is the evidence, the second reason is what results from that. So now you can mention intermolecular forces. I don't know if I'm making sense, guys. That's actually very important. The first reason is based on evidence, and if it's 2 marks, they give you 1 mark for choosing the answer, 1 mark for the reason. So just stick to that. So you're gonna say HCl, and the reason is that amongst all those molecules, HCl is the one with the lowest boiling point. And you wanted to justify your answer, I think, and you're gonna say boiling point. If boiling point is high, I mean it's low in this case, it means vapor pressure. Come on, it means vapor pressure is high due to inverse proportion. So that's how you can justify it, just to make sure that you do get the mark. Which one of the hydrogen halides have the strongest intermolecular forces? Which one do we pick?
The first one.
First one, okay, that's HF, or you can say A, because they also have like A to D, but I will specify and say HF 3.2. It's HF, and if they wanted a reason, you're gonna take that from the evidence. It is the highest boiling point. That's it. Highest boiling point. And you can justify that reason and say, if the boiling point is high, then it means the intermolecular forces are strong. Does it make sense?
Yes.
All right. Okay. See, we moved past 11, but I'm trying to get at least to like one question on stoichiometry and stuff, but if you need to leave, you can let me know. 3.4, draw a line graph to represent the boiling points of the hydrogen halides for 6 marks. I mean, you get a table, you need to just draw the information, and you get 6 marks for that. It means there's some things that you need to remember so that you don't lose any mark. One of the things is the heading of the table. Every table should have a heading, right? Okay, no one is responding, but the second thing is the label. Every table has to have the labels. And then another thing is the correct scaling of the values. I can't go from 0 to 10. That's fine. But then from 10, if I'm using this kind of scale, I can't say this is 30 because it looks like my spacing are 10 units. So I should say 20. And I can't say this is 50. Or one most horrible thing you can do is to say the first value is negative 85. The second value is negative 67. Third value negative 35.5. Last value 19.4. You're just taking the values on the table. So you get a 0 for scaling and even maybe for the shape of the graph. So just make sure you get the correct scaling. It does not have to stress. You don't have to take a ruler and measure. No. As long as the scaling is good enough, I'll show you how I'm going to draw it. Maybe I should have made some space here. Let me just pull it down. Do it some more. Okay. Trying to put that back. Okay. So let's draw the graph. I'm having negative 85 all the way to 19.4. So if I am to draw the graph, I'm just gonna do it like this. Insert the graph. Okay. So I'll go from negative 85. You see this line here doesn't represent 0, or if I want I can put it on 0, that's fine. But anyways, I'm gonna go from not really negative 85, maybe negative 90, and then I can increase my scale by whatever value I choose. I just choose that value. Let's say 20. So negative 70, negative 50, negative 30, negative 10, and then there's gonna be 0 somewhere, and then it goes up to positive 10, positive 20. Okay, now I'm losing my scale. Positive 30 there from 10, because I'm using 20, and then from there I'm gonna go to 50. All right, yes, Kanya.
So I need to go now.
You need to go. Okay, that's fine.
Well, enjoy the rest of your weekend, sir.
Thank you. Same to you. All right. So then, the heading of the table, very important. You're just gonna say it's boiling point versus hydrogen halides, or boiling point of hydrogen halides. You're gonna say it in full words. Boiling points of hydrogen halides. That's what they are giving you on the table. You get a mark for that, remember. Then you're just gonna plot your values. I mean, that you can do on your own, but on the x-axis you can have the first one is wait, let me just quickly go and check. First one is HF, HCl, HBr. So HF HCl, HBr, and the last one is HI. Then you're going to plot your points. The first one, I think it's like 19,4. So that's about here. The second one is negative 85. That is about here. Another one, HBr, don't remember, negative 67. Negative 67 is about there. Then the HI is negative 35,5. That is about there. But you can use the scale of tens just so that your graph looks good. But at the end of the day, you have this kind of situation, and it does not need to be smooth because this data is independent of each other. Like the boiling point of HCl does not depend on the boiling point of HBr. So I'm not gonna get a smooth curve like that, no. And I'm not gonna get a line of best fit. I'm not gonna get a line of best fit like this. Even if the points were like that, I think this is what I explained in the video that we did this stuff. Then I'm gonna connect the points like that because it's independent. If it was dependent though, if the data represent the outcomes of the same kind of experiment that is related, then I might need to do a line of best fit, which is just something like that, just the trend of how the data is. Okay, but I think that makes sense. Let's move on. Try to be quick this time. Compare compounds A and B. Refer to the type and strength of intermolecular forces and energy needed to explain the difference in boiling points between hydrogen halides. So we have hydrogen halides. We need to talk about the strength of the intermolecular forces that we find between hydrogen halides. And it might not be the same intermolecular force. Depends on which ones you're talking about. In this case, we are looking at A and B. So remember, there is a sequence that you need to follow when you explain this kind of questions. And I explained that nicely as well in the recording. So I'm always referring you to the recording because I know that it was very, very nice and effective. But looking at this, you have HF. What intermolecular forces do you find between that?
Hydrogen bonds.
Hydrogen bonds. Good. And then you have HCl. What intermolecular forces are between that?
Dipole.
Dipole. There we go. So the way you explain this, you're gonna say this is 3 point. This was 3.4. This is 3.5. You're gonna say, okay, your first one is HF. You specify the intermolecular forces that you have. Hydrogen bond, you already have 1 mark. Then you go to HCl, you specify the intermolecular forces that you have. Dipole, you already have the 2nd mark. Then the other 2 marks are from comparison. Which one is stronger between the two?
HF.
Yes, so hydrogen bonds in HF are stronger than the dipole forces. Dipole forces in HCl. That's another mark. The last mark Do you know where the last mark is gonna come from, or the last statement you need to write?
No.
Okay, look, read the question again. So if you're unsure of what to write, you read the question again. What do they say? You can read it out for me.
Comparing compounds A and B refer to the type and the strength of intermolecular forces and energy needed to explain the difference in boiling points between hydrogen halides.
Okay.
The energy.
Oh yes, it's the energy. So you can also mention boiling point in there. So we did talk about the comparison. We talked about the type of intermolecular forces and the strength. Now we need to talk about the energy. So you're gonna say more energy is needed to break the hydrogen bonds. I'll just say the hydrogen bonds in HF. Then you can add on, say that's why it has high boiling point. Now you mentioned everything. Does it make sense?
Yes.
Okay, so you get a mark for comparison and the type of intermolecular forces. You get a mark of saying which one is stronger. You get a mark for the energy part and the reason why the boiling point is going to be high for HF. And that's 4 marks in total. It can even be 5. So for this one, for the graph question, you get a mark for the heading. You get a mark for the label and correct spacing. So 2 marks already there. You get a mark for drawing the line graph. I mean, who can draw a bar graph, but that's a mark for the line graph. And then you get a mark for plotting. If I check, this can qualify to be 19.4. If I check, this can qualify to be 85, negative 85, or is it 87? I'm not sure. This can qualify to be whatever. And I check the last point, it doesn't qualify to be 35,5. Then you lose a mark for that, for the plotting. But you will get 1 more mark for plotting the other points correctly, but you lose a mark for plotting another point wrongly. But if all the points are correctly spaced, I mean correctly plotted, then you get your final 2 marks, and that's 6 marks in total. Okay, is that good enough?
Yes.
All right. So that concludes question number 3. Any questions we have on this?
No.
All right, good. Then this one is on ideal gases, and I kind of feel like maybe this one is easier. You got it most of the time, but it looks like there's a longer question for 5 marks, so maybe we can look at that. The diagram below shows a sketch graph of the product PV against P for 1 mole of oxygen gas at 0 degrees Celsius. That's the solid line. The dashed line represents the same relationship of 1 mole of an ideal gas. So it's the same oxygen gas, but this time it's ideal. Then it means the one in a solid line is the actual real gas. Okay. Then the first question, what is meant by the term ideal gas? What would you say there?
I forgot the definition. Can I try?
Yes, go ahead and try.
It's a gas that obeys all the gas laws.
All right, that's good enough. But if you want to make sure then you should say, because it's not a real gas, it's a hypothetical gas, that obeys all gas laws, for any temperature and pressure, or at any temperature and pressure. That will be a smart answer, because now there's no way they can mark you wrong. Or instead of any, let me say at all pressures and temperatures. Oops. At all pressures and temperatures. That's the definition of ideal gas. But again, before you go to the test, you go and check it out. See what your textbook or what your notes say. Okay. 4.2, exactly 3 moles of gaseous compound occupies a volume of 12 decimeter cubed at 15.8 degrees Celsius. Calculate the pressure of the gas at this temperature in kilopascal. Okay, this one is on what we call the ideal gas equation, and I'm not sure you guys did it this year, because this question paper is from 2022. So if you didn't do it, if you didn't use this equation, then we don't need to answer this question. Did you use it or no?
We did.
You did use it?
Yes.
Oh, okay. I was under the impression that you guys didn't do it. Okay, anyways, we're gonna write your given data from here then. Given data. I'll start with the constant R. That one is from the periodic table. We don't need to guess. I mean, from the information sheet. Go straight down and check the value. Also the units. 8.31 joules per Kelvin per mole. Okay. R is 8.31 joules per Kelvin per mole. Awesome. I'm also given the volume, 12 decimeter cubed. Then my question now is, do we substitute it as 12 decimeter cubed, or do we have to convert?
You substitute it as it is.
No. That's a big error. One thing, I know we didn't do this because I thought you only do Boyle's law. This one is not Boyle's law, it's like the ideal gas law. But one of the most important things for using this equation, most important, is the units. We're no longer gonna use any units. We need to use SI units. And let me say specific units, because if I say SI, you might say, but decimeter cubed is SI, because in chemistry we use decimeter cubed. But for ideal gas law, very important, pressure is going to be in pascals, not kilopascal, but pascals. Volume, not in decimeter cubed, but meters cubed. Please don't forget that part. N is pretty standard, it's going to be in moles. R is a constant, so the units are already given. Temperature is going to be in what units?
Kelvin.
Kelvins, yes. So that's the units that you need to remember. Pressure, Pascal. Volume, meter cubed, not decimeter. N, moles. T, Kelvin. Alright, so to convert decimeter cubed to meters, you need to divide by 1,000. I mean, 1,000 is not hard to remember. If they give you, for some reasons, they decide to give you 12 centimeter cubed, you can take this to decimeter by dividing by 1,000. take it further to meters by dividing by another 1000. I think it's going to be 2 zeros, I'm not sure. 1 2. Okay, then that's now in meters cubed. Does that make sense?
Yes.
Okay, good. Remind me to send the notes at the end, because I might just say you guys are fine, but maybe you need the notes. Okay, then now that we have the volume in the correct units, let's look at the number of moles. We are given number of moles, it's 3. It's already in mole, so that's good. The T is not in Kelvin. How do we get it to Kelvin?
You add 15,8.
15,8. Or you
Or
said,
you add it to 273.
oh yes, we add 273 to that. We get how much?
288,8.
288,8. Now it's in Kelvin. Then we can go and substitute and solve. So sub and solve. And now the equation PV and RT, just substitute everything. We're looking for pressure, so volume 0,012, moles 3, R 8,31, T 288,8. Okay, then what do we get for pressure?
For 599,982.
Okay, then the units?
Pascal.
Pascal. Good. Or you can even convert it to kilopascal, then you're just gonna take it as rounded off, and that's kilopascals. Then you're good. The way they'll mark it, obviously they won't give you a mark for given data, but that is just helping you. They'll mark the equation, they'll mark the left hand side, they'll mark the right hand side, and then they'll give you, oh, they actually specified to write the answer in kilopascal, so the last mark will be for the kilopascal. Oh, okay, because the answer that you get is in pascals. So if you write that and you write the units, if you forget to write this Pascal, then you lose that mark. And for taking this to kilopascal, then you get the last mark. So 5 marks in total. Okay, then I'm sure you already know which question they will have even before I read it. Okay, maybe not quite. Let me see. If the volume of the container in the reaction in question 4.2 is doubled, what will happen to the pressure? That one is pretty straightforward. Volume and pressure are directly or inversely?
Directly.
No, it's actually inversely. That's one of the, like, in Boyle's law. Remember I did Boyle's law. That's the only thing you need to remember. Like, if I have this container and I close it off like this, then the pressure is low because the volume is high enough. But if I take this thing and press it more on the container, then I get more pressure because the volume is now too low. So this relationship is one that you should not forget. Then if I double the volume, it means the pressure should be low. So to answer this question, pressure decrease, and to reason, let's say question 4.3. The pressure will definitely decrease due to inverse proportion. The reason is the inverse proportion. So you're just gonna write that. Then just specify it at any constant temperature. At any constant temperature. That's like the definition of Boyle's law. Do you remember it perhaps by words?
No,
You don't remember it?
I don't.
Okay. All right. But what it says is that the pressure is inversely proportional to the volume at any constant temperature. Okay, so they'll give you a mark for decreases. They'll give you a mark for that reason. So 2 marks. Okay, let's see how many more questions are left. Okay, it's a couple. But I'm sure if we do question 5, then this one, you remember we did this one in class, right?
Yes.
Yes, and this is acids and bases. You just let me know if you want us to do it. This is redox. Also, you let me know if you want us to go through that one. Question 5. Unless if maybe you think you're tired to continue from here, then maybe we can stop and try to do it on Sunday. So tomorrow I am available. Or should we at least do question 5?
We can do question 5.
Okay. All right. Maybe I need to move things around a little bit because I'm not gonna have the space to read the question and also to do the solving. Yeah, I can just move it down. It's fine. Okay. Then I'm gonna need to take all these and move them up. Okay, cool. So this was question 4. Then question 5, you can read this statement for me. Let me just move it back to good position. Okay, I can read the statement for me.
Brisk effervescence is seen when diluted hydrochloric acid reacts with sodium carbonate. The balanced equation for the reaction is.
Okay, thank you. All right, if we can just check the information that we can extract from the statement. Let's see, a brisk effervescence. Okay, I've heard of that word, but I'm not sure what it is. It's seen, I think it's a color though, maybe. It's seen when dilute hydrochloric acid. Maybe there's something that it's going to do with that dilute part. Reacts with sodium carbonate. Sodium carbonate. The balanced equation is this. There's sodium carbonate plus hydrochloric acid, which gives us these products. Remember, they can maybe not give the products and ask you to do it. And you remember when we did acids and bases, I remember it was only you in the class. We said a metal carbonate plus an acid will always give a salt, carbon dioxide, and water. Okay, 3 products. Every time you see carbon in the salt, it means there's carbon dioxide. Okay, that's the one thing I used to forget in my high school days. Just make sure you remember that part. Okay, first question, 5.1. Write down the formula of the substance that causes the brisk effervescence that is seen. So it's basically the color. Brisk effervescence. But looking at this, which one do you think is gonna cause that? Let's say you don't know even what that is, but you need to guess.
Sodium chloride.
Sodium chloride. Okay, that's a good guess. But maybe if you go to Google and check what actually brisk effervescence is, they say a chemical reaction that produces a rapid release of gas bubbles, usually carbon dioxide in a liquid. Okay, so my guess was that it's a color, but it's actually bubbles that you see just bubbling in the liquid. So like this is the liquid, it's our products, but within the products there's like bubbles that are just going crazy, and that can only mean there's carbon dioxide. It's like in Coca-Cola. So that is what we'll call a brisk effervescence. Okay, at least now we know CO2 is the answer. All right, 5.2. In a reaction, 10.6 grams of sodium carbonate reacts completely with excess hydrochloric acid. So it means you don't need to find the limiting reagent. You already know which one is the limiting reagent. Which one is the limiting reagent?
Sodium carbonate.
Yes, because the acid here is in excess. All right, that's good. Then we know that for any calculation we need to perform, we're just gonna use that value that they give us. There's no need to calculate the limiting reagent. First question is define a mole.
The amount of substance having the same number of particles as 1 mole carbon, the 12 grams of carbon.
All right, very good. So amount of substance. Yeah, it should feel illegal not to know the definition of a mole in chemistry. So I'm just say having the same amount of molecules as in 12 grams of carbon 12. If you mention that, then you get your full 2 marks. If you miss the having exactly the same molecules as 12 grams of carbon 12, then you might lose 1 mark. Oh, in grade 11 especially, you lose all the 2 marks if you miss something that is important. So amount of substance is important. Having the same number of particles or molecules as 12 grams of carbon 12 is equally important. So you get 2 marks if you mention those 2 points. Okay. Then 5.2.2. Which substance is the limiting reagent? Give a reason. Okay, we said it was Na2CO3, but what is the reason for that?
Because we were told that it reacts completely.
Okay, they said it reacts completely. What other thing can we say? They also said HCl is
in excess.
good. Yeah, just make sure you mention all the points that you can see, just so that you don't lose the mark. It's 2 marks, which means they're gonna give you a mark for the answer and the reason that you give. So 2. Okay, cool. 5.2.3. We are on a good pace so far. I'm happy. Calculate the mass of carbon dioxide produced during this reaction for 5 marks. That one is free 5 marks, isn't it? Don't you think it's free 5 marks?
It is.
Yeah, there's no way you can get it wrong, unless if maybe you mess up the molar mass. Okay, let's get the process. What's the first thing we do?
You can find the number of moles for the sodium carbonate.
Yes, sodium carbonate moles, because we already have the mass. So N is equals to M over M. Then when I substitute, I need to specify which moles I'm finding. Otherwise, the marker will think that maybe that's your final answer. So I specify in bracket that I'm looking for moles of sodium carbonate, and I put the mass on top, 10.6. I need to calculate the molar mass. Sodium, let me just scroll down because I can't remember. I think sodium is 23 or something like that. Okay, sodium is, oh, I actually hid it there with that, but it is 23. There it is there on group 1 on the corner. So let's do 23 times 2 plus 12 plus 3 times 16.
Zero comma 1 moles.
Oh yeah, that's the final answer. Okay, what is the molar mass though? I guess to get 0, 1, it means it has to be 106, but you'll check for me.
It is 106.
Okay, awesome. So we get 0, 1 mole. And if I'm marking, I can see that, okay, that's not the number of moles of CO2. That's the number of moles of carbon, of sodium carbonate. Then that's good. So step number 2, what do we do?
We can find the ratio, the amount of moles the carbon dioxide has by
Using
doing ratios.
the ratios. Good. So we go to the ratios for moles of carbon dioxide. Awesome. And it's just go to the formula, to the chemical reaction formula quickly. It's 1:1. Okay, so but then even if it's 1:1, you already know the answer, but you need to show the ratios. That's actually where a lot of learners lose marks, because as soon as they see the ratios the same, they just say, I can just skip that part and just show the answer. But you need to show that part. I can show it like this, that's good enough. Or I can just go and say, so this means the number of carbon dioxide, then I'm specifying, is also 0, 1 mole. All right, what is the last step?
You can find the mass.
Can find the mass at this point, yes. Okay, let me move this down a little bit. And okay, so we found the moles. Now we need to find the mass pretty straightforward question, and there's always so many of these kind of questions. Where you just do the exact same thing every time to get the marks. So now step 3, mass of CO2. Then it's the same equation we started with, n is equals to small m for mass over big M for molar mass. Then I can rewrite the equation this way to just find the mass of CO2. Number of moles times molar mass, I can substitute. Then what is the molar mass of CO2?
44 grams per mole.
44 grams per mole, good. So this will give me 4,4 grams. Alright, very nice. Then we'll go to question number 5.2.4. Calculate the mass of sodium chloride if 4,87 decimeter cubed of carbon dioxide is produced at STP. Okay, calculate the mass of sodium chloride if we produce this amount of carbon dioxide at STP. Okay, to me, this question is not very smart because I don't need to know the products of carbon dioxide in order to find the mass of sodium chloride, because I already know the moles of sodium carbonate that completely reacted. But anyways, we'll follow what they want us to do because already we know what they want us to do. I'll write it here, 5.2.4. They want us to use the number of moles of carbon dioxide, V over Vm, or I guess maybe let's say the results are not related, so we can't really use the number of moles of CO2 that we have or anything else. So we need to use whatever they give us, 47 over, they didn't specify Vm, so we're just gonna take it from the information sheet, and that value is 22,4. But very importantly, again, we use this equation only when we are dealing with a gas. Doesn't matter if they say it's STP or not. As long as it's a gas, we can use this equation. Okay. What do we get when we divide?
0.2.
0.22 mole. Cool. Then we just need to do the ratio quickly. So it's gonna be CO2 versus NaCl. Now remember, we have two NaCl's. So if I have 0.22 here, I'm gonna have 2 times that, or I'm just gonna put this as x, cross multiply. Then I'll see that my x becomes, and then at this point I'm just gonna write it as number of moles of NaCl is 2 times 0.22, which gives us what? Is it 0.44?
Yes.
Okay, good. Then the last thing I'm gonna need to do is to use the moles is equal to mass over molar mass. That will help us find the actual mass. Okay, so it's the exact same kind of question, except they are not using the given data that we used to have. They're just giving a different product. Then for the mass, I'm gonna have this equation in this form already, because I know I'm not gonna get a mark for that equation at this point because I already used it. What is the molar mass of NaCl? Na is 23, Cl is 35,5.
58.5
50,
grams per mole.
58.5 grams per mole. Good. Then the moles are, the mass.
25.74
25.74 grams. Okay, good. And how they'll mark is, it's 5 marks, so they give you a mark for the number of moles of carbon dioxide, and the equation, because it's the first time you are using this one. Then they'll give you a mark for the ratios, a mark for the number of moles of this thing, and then the mass as well. So 5 marks in total. Okay, also stoichiometry, pretty simple. So if you were guessing all along, you know that this 10 marks, I already have it 100%, this one. So that's a very good thing to know. Then when you move on to the next questions as well, you already know how many marks that you are 100% sure you got. Obviously, you're gonna get more, just that for those kind of questions you are very, very sure. Okay, the empirical formula of a gas is NO2. Exactly 46 grams of this occupies 11.2 decimeter cubed at STP. Okay, state Avogadro's law that you will use with this information. It's definitely the definition, they just put it in a weird way. How do we define Avogadro's law?
I forgot it.
Okay, it's just basically what the equation says, and what it says is that 1 mole of a substance, in this case a gas, will occupy, not occupy, because Avogadro's equation says N is equal to number of particles over Na. So it will have those many particles. They also give us, I don't know if V over Vm is also Avogadro's law, but I'll check. You'll also help me there. But Avogadro's law says 1 mole will have 6.02 times 10 to the power 23 molecules. But there's a possibility that this is also from Avogadro, but we'll check. Because in this case we are actually going to be using the Vm equation, just looking at the fact that this can be, this is a gas, they do say that. So that's why I feel like we need to define this equation, which would say that 1 mole of a substance occupies 22.4 decimeter cubed of volume at STP. But I'm not sure if it is to do with Avogadro's law, but again we'll check that. Okay, fine. 5.3.2, find the molecular formula of this compound. What do you think we need to do?
Not sure.
Okay.
There must be a formula, but I don't know how to.
We must use the formula. Which one?
Find it.
Or find the formula. Okay. It's pretty easy. The way I see it, remember, if they want you to find the molecular formula, do you remember the process? I actually explained that one a lot. We need to take the molecular formula, the molecular molar mass, and divide by the empirical molar mass. Do you remember that?
Yes.
Yes, then whatever answer we get, we multiply by the empirical formula to get the molecular formula. So we can find the molecular molar mass by using those information that is given. They give us the mass and Vm. So first we can find the number of moles because it's a gas. So number of moles is V over Vm. 11,2 over 22,4. What do we get?
0.5 moles.
0.5 moles. And actually the grams themselves could have helped us to find the moles. So maybe there's two ways to kill a cat here, or whatever they say. Let's find the number of moles using that. Or they say 46 grams occupies this volume. So we know it's 0.5 moles for that. So I guess we can just find the molar mass. Yeah. The number of moles is mass over molar mass. This means the molar mass is mass over number of moles, which is 46 over, we have the number of moles, 0.5. Then what do we get? We get
92.
Or 92 grams per mole, because that's the molar mass. Then we need to find the molar mass of the empirical formula, and that's NO2. So molar mass of empirical is equal to N. Nitrogen is like what? 14 plus 16 times 2 for oxygen. So we get how much?
46 grams
46
per mole.
grams per mole. Okay, then we can find that ratio. Maybe we didn't have to like do it this way, but still that works. Maybe there's a simpler way, but anyways, we do what we know. I'll just call this R, and it's the molecular mass, the molar mass divided by the molar mass of the empirical. And that's 92 over 46. What do we get?
2.
Then we multiply that empirical formula by 2, so NO2 by 2, everything by 2, it becomes N2O4, and that's our molecular formula. Okay.
Can you repeat everything again?
Can I explain everything again?
Yes.
Sure. So we are given, if we read the question, they say the empirical formula of a gas is this. So what I extract from that is that I'm given the empirical formula, fine, and they say it's a gas, so I can use N equals to V over Vm, and then they say there's 46 grams. That's what I just take. It's the mass of this molecule, and they say it occupies a volume of 11,2. So I can just find the moles by using that Vm, that V that I have, and knowing that it's a gas. So I'm gonna do that and find the number of moles of this molecule, and because I also know the mass, I can then think about the molecular molar mass, because if I know the mass of this thing and the number of moles, the molar mass that I'm gonna get is the actual true molar mass of the compound. So that's just given information. So I'm just gonna write the molar mass equation in this form by making big letter M the subject of the equation. This 46 is given as the mass, and then the number of moles that I already know is 0.5. I calculated. Then I get the molar mass of the compound. So this is usually the information that will be given in an empirical formula question. So what we were doing here is what is normally given if they ask you to find empirical formula. But then from that point, when I know the empirical formula, I can find the empirical molar mass. And when I find that empirical molar mass, I need to divide it, or I need to take the molecular molar mass, the actual molar mass, and divide by the empirical molar mass to get a ratio, which I'm going to multiply the subscripts to get the actual subscripts in the molecular formula. But I think from this point down, it makes sense. But from the first point, we're looking for the molar mass using the information that we have. I don't know if it makes sense.
Makes sense.
All right, very nice. So yes, it's 3 marks, which means maybe our method is too long, but who cares if it works, right? So how they'll mark this is they'll give you a mark for finding the number of moles. They'll give you a mark for probably the molecular formula or the ratio. Then the final mark will come from the molecular formula. So 3 marks. You could have just used you know, the VM and the grams can give you the number of moles already. And looking at the empirical molar mass, you can see that the number of moles that is true is 0.5, but from the empirical molar mass, let me call it empirical number of moles, you get 1, because you'll have mass over molar mass, and the mass is 46 from what is given. The molar mass that you calculate is 46. You get 1. Then you can say, okay, the actual value is 0.5. The empirical value is 1. So it means there's 2 that I need to multiply in order to get the correct molecular formula. But I don't advise that because I'm sure you don't understand. But that method that I just did is good enough because it also takes you to what you need to do for molar mass for empirical formula questions. Then one more thing I need to mention for empirical formula is that if you don't get a actual whole number ratio when you divide by the smallest, you remember to just test small values like 2, 3, 4, 5, 6, 7 to try and make it a whole number. And we say that if it's maybe the ratio is 2,1, that's good enough. You can just round off to 2, 2,2. Maybe you can try to multiply, but if you feel like, nah, this is not good, then you can just round off. But when it starts to be 3 and 4 and 5 and 6, 7, then that way you should multiply by some value to get it to a whole number. But you know what I mean, right?
Yes.
Okay, cool. Then this question again is on endothermic and exothermic reactions. I believe this one should be simple. We already talked about it, so I'm just gonna skip that one. Let's see if there's any difficulty on this acids and bases. I know what, maybe let's go to the last question, see what we can do, because it's short, it's 9 marks, and maybe we can try to finish off the acids and bases question. I'm not sure. It says the lab assistant stored zinc sulfate in an aluminum container. After a while, the teacher notices that the aluminum container is eroding and she suspects a redox reaction. The teacher writes down the following unbalanced reaction. Okay, so basically taking a aluminum container and we're putting zinc inside. And unbeknown to us, zinc can react with aluminum by redox reactions. So what we're gonna see is that the container starts to erode. So there's like holes being eaten away from the container there, which means the zinc is gonna flow out at the end of the day. All right. Then if we check out what really happened is that we have a reaction between zinc sulfate, which can be written out as zinc 2 plus, and aluminum, which is Al solid. Zinc 2 plus is zinc aqueous, and I'm removing the the SO4 because it's a spectator. So zinc 2 plus aqueous, and then this gives us aluminum, and there's two of them. Aluminum aqueous will be 3 plus, and zinc solid. So maybe I need to move this a little bit to that side. Just make space. But obviously the tables of reduction potentials will help you to identify the ions. So if you don't know that aluminum is 3 plus from the periodic table, or just from your knowledge, you can use those tables to see the ions and how many electrons it gives away and stuff like that. Then we also have plus zinc solid. And if I were to balance, I see that I just need a 2 in front of the aluminum there, and looks to me like everything is balanced now. Maybe not. Yeah, it's not balanced because I didn't take note of the SO4s, that in this side there's 3 of them, in this side there's only 1 of it. So once again, it goes down to how we are going to balance the electrons. I'll just call this one a skeleton net reaction. It's not complete, it's not balanced. So you just need to do some work on it, but it's quite easy. Define a redox reaction. Do you remember?
No.
Okay. Then that's one of the definitions you need to remember to mark down so that you can revise. But it's just a reaction that involves electron transfer. So there's electron transfer in redox reactions. One thing is going to lose electron, another thing is going to accept electrons. So we say the electrons are being transferred. Okay, 8.2.1. This is where we need to just fill up everything now. So it's all up to us. We are having zinc and aluminum, so we can just use the tables to just finish off this whole thing. I'll use 4B because I think that's the one you guys use. Aluminum and zinc, and we have to be careful to pick the correct ones. Zinc should be zinc to zinc 2 plus, which is this one. Aluminum should be aluminum to aluminum 3 plus, which is this one. Okay, what did we say? We said, okay, which one will be oxidation and which one will be reduction according to you, according to what we said?
Aluminium.
Okay, let's put it this way. Which one stays the exact same way we find it in the table? Remember, it's that thing we really emphasized. I even typed a message in the group and I pinned that message. It's still there in the group and it's still pinned. So if you're not sure, then maybe you can go and check in the group that pinned message from whatever term. But I still remember that we actually had a struggle that day, and I was like, no man, this is too simple to forget. Maybe I'll just pin it for you. What did I say in the pinned message, if you can read?
on the tables of standard reduction potentials, the half reaction with the most positive stays the same way. For example, undergoes reduction. The half reaction with the least positive, that E thingy, compared to the other half reaction must be swapped. For example, undergoes oxidation.
Exactly. So you go and look the E naught, it's called E naught, but it's fine. And you'll see that negative 0.76 is the most positive or is the least negative. So it's the higher value. It means zinc 2 plus 2 electrons becoming zinc stays the same, stays the exact same way we find it on the table. The other one, because the E naught is small, it has to be swapped. So I'm gonna say aluminum becomes aluminum 3 plus 3 electrons. That's it. Then if I have to do the net, I just need to balance the electrons, right?
Yes.
How do we do that?
Find lowest common factor.
Yes. And
It's
that
gonna be
is 6. Okay. Then what do we do?
we multiply the zinc reaction with the 3, then you multiply the aluminum reaction with the 2.
Correct. So what I like to say is that usually it's between 2 and 3 usually. So I just need to say the one that is a 2 I multiply by 3, the one that is a 3 I multiply by 2. That way they are all 6 electrons. So the electrons are going to end up being 6 on each side. Then we have 2 for aluminum side, 2, 2, 3, 3. Then the electrons cancel. I just pull everything down. 3 zinc 2 plus 3 aluminum solid gives 3 zinc solid plus 2 aluminum 3 plus. And that's the correct balanced.
2 aluminum.
You say? Oh, 2. Yes. On the reactant side, yes. 2 aluminum. Okay. And all the questions are going to be based on that. They're just gonna ask for the half reactions, maybe even the reducing and oxidizing agents, and the net ionic. That's it. So let's paste everything here and just call this, it's 2.8.3, but oops. Okay, what I'm gonna mention is that after you do this work, when they say write the oxidation half reaction, you're not gonna include the balanced stuff. So maybe let me remove them for now. The balancing is not included in the half reactions. You're just gonna write them exactly how you find it in the table. For oxidation, we have aluminum. So take that away and put aluminum up. That's the loss of electrons. For 8.2.2, they want the reduction half reaction. So this is the one of gaining electrons. Put that there. 8.2.3, they want the net. And that's what we just did there. Okay. That's quite straightforward. And if they ask for reducing agent, oxidizing agent, you go to the reactant side, aluminum, because it's oxidized, it's the reducing agent. So that's the reducing agent. You go to the reactant side, zinc, because it is reduced, it's the oxidizing agent. Oxidizing agent. Okay, and that's actually 8.3. They say identify the reducing agent. That's the one that is oxidized. And if they want a reason, because it is oxidized. Okay, pretty straightforward. A question might be, will the reaction in the container react? Maybe they have something other than aluminum. Then we're just gonna check on the reduction potentials and identify the one that is a stronger reducing agent, which one is a stronger oxidizing agent. For example, if I go down table 4b, this aluminum is a stronger reducing agent. And you can see that from our analysis, aluminum is a reducing agent. That's what we said. And zinc, you can see it's down, so it's going towards this arrow. It's a strong oxidizing agent. That's what you say. Then due to that reason, there will be a reaction. But if it's swapped, if zinc was on top, let's say instead of zinc metal we used magnesium, which is just on the top. So magnesium itself, compared to aluminum, it wants to be a reducing agent, while aluminum will be an oxidizing agent. So a reaction will not take place. Why? Because this aluminum equation will stay the same, while the Mg will have to swap. So if we start with aluminum solid, you can see from this reaction we don't start with aluminum solid, so that reaction will not work. Compared to the first one, do we start with aluminum solid? Of course, we start with aluminum solid. That's why this reaction will work. Okay, if it doesn't make sense, just make sure you rewatch the recording. Understand that if aluminum were to swap, then we're going to have aluminium 3+ gaining 3 electrons to become aluminium. Then this means we actually start with aluminium 3+ instead of aluminium solid. So that's a nonsense equation. It means the reaction will not happen. To give a reason, you're just going to say one is a strong oxidizing agent, another one is a weak oxidizing agent, reducing agent, or stuff like that, and then conclusion, a reaction will not happen. Okay, that's the chemistry way of putting it, but in terms of the way of understanding it, that's how you check. Another example they can give, let's say they put zinc sulfate, which is zinc 2+, in here. Then they say, okay, we are placing iron nails. This nail is iron, Fe. So it means we start with Fe solid. But if you go to your tables and you see that it actually starts as Fe 3+ to become Fe solid, then you know that the reaction will not happen. It will happen only if it's Fe solid to Fe 3+ compared to zinc. So zinc will decide. Maybe let me do it for you so that when you think about it in revision, then you know what the answer is what the answer is actually. So I'm going to mark the half reaction for zinc. Where is that zinc? We had it 0.76, I think was the E naught for zinc. Yes, negative. I'm using a different table this time, but again we're just referring to the E naught values. Then Fe 3+ to Fe. You see this one that I'm gonna do in zigzag is not the one that we're looking for. because that one has Fe3 plus and Fe2 plus. That's not the one you're looking for. So do not make that mistake of taking what that is actually not correct. So I'm gonna go ahead and look for Fe3 plus and Fe, and there it is. I saw it, so I'm just gonna use light blue to highlight it. Oops, wait. That's the one that we're looking for. So if we write the half reaction, tell me which one is gonna be a reduction between the two. Are you not sure?
Yes.
You're not sure? What did redox reactions do to you guys? I'm so confused because we just went through it now. We just read the message in the WhatsApp group now. So I'm so confused. The one with the most positive E naught stays the same. Come on, the one with the most positive E naught stays the same. That's it. That's all you have to remember. So this one stays the same. The one with the least positive, it swaps. Okay, I'm losing hope a little bit because this is really supposed to be really easy. So it means this one is oxidation. I mean, it's reduction. Oops, what is going on? My pen is getting tired. Okay, we have 2 plus here. This is reduction, this is oxidation. So the nail was a solid, and here we see we start with the aqueous. So the reaction will not happen. You can go and Google and even check, will a nail in a iron nail, iron nail, iron is written as iron nail. Come on, I'm writing. A iron nail will not react in zinc. Will not react in zinc sulfate. Yes, that's the conclusion. Let me go to Google and ask quickly, will iron nails react in zinc sulfate? Okay, the answer that I get is a big no. So it just says no. Iron nails will not react in a zinc sulfate solution. This is because iron is less reactive than zinc according to the reactivity. Okay, they just go through like some advanced chemistry, but from our chemistry, from where we are standing, we just need to use the table, and we're gonna say iron, or I'm gonna say zinc is a strong reducing agent than iron. Therefore, there won't be any reaction. That's all. That's the reason that I need to give. That's all. Okay. Awesome. All right. We are almost at the end. I just need to know if there's a problem here. You know what? Maybe we can just do it, and then we'll leave all the time for you tomorrow to do all the remaining revisions. Okay. Just want to make space a little bit here for this one. So the only chapter we couldn't do today is only redox, exothermic and endothermic reaction. Sorry, that's the only ones we didn't do, but I assume that you will revise them. Quite easy and straightforward. And also intermolecular forces, do watch the video, please. Okay. Question number 7. When sulfuric acid reacts with water, it ionizes in 2 steps, as shown in the 2 balanced equation. We went through this again. It says that hydrochloric acid, not hydrochloric, sulfuric acid reacts in water. It's going to give away 1 proton to become HSO4 minus. And we're going to take that HSO4 minus, we put it in water again, it gives us SO4 2 minus. Therefore, you can identify your conjugate acid-base pairs already. We know that H2SO4 donates a proton in the first reaction, so that's definitely an acid. I mean, we already know that. It means water should act as a base. Conjugate acid, we need to call it conjugate. So H3O plus is our conjugate acid, and those 2 are friends. And HSO4 minus on top is our conjugate base, and those 2 are friends. They are conjugate acid base pairs. Okay, you can do the same on the bottom, already indicated, but now you check and see that water still acts as a base, so that's not an alpholite. A lot of people can make that mistake. Conjugate acid, conjugate base. These 2 are conjugates. These 2 are conjugates. Give Laurie Bronsted definition of an acid. How do we define an acid according to Laurie Bronsted?
A proton donor.
All right, 7.1.1, acid is a proton donor. Good. That's Laurie. Laurie Bronsted theory. I guess you also remember the Arrhenius. What does it say for an acid?
A substance that produces hydrogen ions in water.
Yes, very good. Hydrogen ions or H3O plus, which is hydronium ions, any of those will be accepted. Okay. 7.1.2, write down the formula of the conjugate acid of HSO4 minus and the conjugate base of HSO4 minus. Okay. Let's see. What do we say for this? What is the conjugate acid of the same molecule? So we're looking at HSO4 minus. They say, first of all, what is the conjugate acid of this?
H2SO4.
Yes, that's correct. So conjugate acid is H2SO4. Turn and move quickly so that we can have time to rest. Then what is the conjugate base?
SO2 minus 4.
SO4 2 minus. Good. Okay, so that's question 7.1.2. 7.1.3. Which one of the compounds in reaction 1 and 2 is an ampholite? Looking at those reactions, which one acts as an ampholite?
SO4 minus.
SO4 2 minus
SO4 minus SO4 or minus, yeah.
Let's see. It should be HSO4 minus, isn't it?
Oh, yes.
Yes, that's the one that can go in this direction. It can become a base. In this direction, it can become an acid. So that's the only ampholyte. Okay. I mean, you can say water technically, but in this specific reaction, water is not an ampholyte. It only goes one direction. All right. Then 7.2. In a titration, Elena finds that 20 cubic centimeter of a 0.2 mole per decimeter solution of sodium hydrogen carbonate. So I'm just going to write those given data down. Volume is 20 cubic centimeter. I need to divide by 1,000 to get decimeter cubed. Concentration 0.2 mole per decimeter cubed. And it neutralizes 12 centimeter cubed of sulfuric acid. So I go to the acid part and say volume of this already divided by 1,000 is 0.012 decimeter cubed. The balanced reaction is this form. That's good. 7.2.1. Why is H2SO4 regarded as a strong acid? It's a theory question. What would you say? So the evidence in this case is not there. It's just theory. Why is H2SO4 a strong acid? So let me go back. Basically, it's how did we define strong acids?
Is it because it
ionizes completely in water? Yes. Do you remember when we said that?
Yes.
Yes, that's the reason why it's a strong acid. And it's a definition of a strong acid, so it's 2 marks because they are trying to ask you to define what a strong acid is. So basically it's define strong acid. Okay, good. Then moving on, almost done here. How many moles of NaHCO3 are present in that given data? This one is straightforward, right? Which equation do we use?
C equals N over V.
Correct. I can make N the subject of the equation. In bracket, I can show that I'm finding NaHCO3, and this will be CV. Substitute 0.2 for C. For volume, it should be converted to decimeter cubed. So 0.02. I see I actually messed up when I was writing given data. Supposed to be 0.02. Just erase there and show that it is 0.02. Then you calculate and tell me the answer.
4 times 10 to the power of minus 3.
All right, 4 times 10 to the power negative 3. What is the units?
Moles per decimeter.
Think again. Remember what we are calculating? Maybe let me write it down instead of there.
Moles.
Moles, yes. I see why it confused you, because this was C equal to, and then I changed it around on the same line. So just put it on the bottom line and you can see that we are doing moles. Good. It's 3 marks, pretty straightforward. It's the equation, it's the substitution, it's the final answer. And 7.2.3, determine the number of moles of H2SO4 that are neutralized by this same amount of NaH CO3. What are they asking you to do?
So find the number of moles of H2SO4.
Yes, by doing what? By using
Ratios.
the ratios. Yes, just go ahead and use ratios. Pretty easy. We get NaHCO3 versus H2SO4. The ratio on the balanced equation is 2:1. Then I know the number of moles of this guy, so I can just put N for the other side. Then if I cross multiply, I'm gonna have 2 times N equal to 4 times 10 to the power negative 3. So the final answer, we can already tell, it's going to be 2 times 10 to the power negative 3 moles. So let me do the cross multiplication first. That multiplies that, that multiplies that. Good old ratios, very easy. 4 times 10 to the power negative 3. Then I specify I'm doing number of moles of H2SO4, and I find 2 times 10 to the power negative 3 mole. Okay, good. Very last question now. This was 7.2.3. Okay, what does the last question want us to do?
Calculate the concentration of the H2SO4 solution.
Okay, it's just a follow-up from the number of moles, so that's pretty easy because we are given the volume. So which equation do we use?
C equals N over V.
C equals to N over V. Good. So it's pretty also again straightforward. Stoichiometry. I find stoichiometry very much like straightforward every time. It's the same things always. Okay, then next line I like to specify because it just shows the marker what I'm doing. Then I'm taking the value that I found previously, I divide by the concentration already, the volume already converted to decimeter cubed. Then what do I get?
0.16.
0.16, okay, mole per decimeter cubed. And that is that. Any question on this particular question?
No.
All right, then yeah, the question paper is pretty much done. What I'll say, go and revise, is percentage purity, because we didn't find it here, and that's the pure over impure. They can go ahead and say percentage impurity. If they say percentage impurity, then you're supposed to say impure, or let me put it this way, impure minus pure, or say sample minus pure, divide by impure or sample. So impure in this case, I'm just talking about the sample, not the mass of the actual impurities. So it's sample. I think it's smart to say the word sample, because if I say impure, it might sound like it's the mass of the impurities. Okay. Then another thing that is to do with percentage is percentage yield, and that one is pretty much actual yield over theoretical yield. Tell you what, the impurities here are given, the sample mass is given. So in this case, they'll give you the sample mass, unless if they do some weird things. But if you know your stuff, then if they come around in like weird circles, you will know what to do. But for percentage yield, we're gonna have actual yield on top over theoretical, and the actual yield is the one that is theoretical. The actual yield is the one that is given. Theoretical is the one that you find using your stoichiometry. I trust that if you go and watch the recordings, if maybe you're unsure of this, but it is one of the easiest topics. Theoretical, multiply this by 100, so we say that actual yield, because it's experimental, it's what I actually get when I do the thing, so it's always given. Theoretical yield, you just need to use stoichiometry, and I'm 100% sure that you can do stoichiometry. So you do the calculation. There'll be like blah 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 plus blah 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 is equal to whatever plus CO2, and then they say the volume of CO2 produced is 2 decimeter cubed. Then what is the percentage yield? Oh, this is percentage purity. So percentage yield, they'll say experimentally we found this much, but what is the yield? In other words, they give you a reactant and they want you to find the product using the chemistry. So say NaCl plus whatever is equal to whatever plus what, CO2, I don't know. Then they give you the mass of this. You want to find the output mass, put it there versus the given mass, divide by multiply by 1,000, you get your yield. Okay, I know it's pretty simple and you'll get it. Yep, that's it for today, and actually that's it for the year, because I don't think we're gonna need to do another lesson. If you have any questions, you can always talk to me on WhatsApp, probably in the group, because you don't need to set up any lesson. I'll be happy to help you out. I'll even make small videos if I have to. For topics that I think are a little bit harder to understand, then I'll make a small video, 2 minutes, then that will take care of that. But yeah, it was very, very, very nice working with you. I really like that you attend. Everything is just perfect. You do your homework. So to close, just have a great time with that exam. Don't be intimidated. Feel free. Apply everything you know. Study for Sunday. And I wish you a lot of good luck for your results also in the other subjects. And I hope to see you again next year in grade 12.
Thank you. Bye, sir.
All right, thank you. Bye.